I do want to talk more about statistical power and how it's calculated. In terms of calculating power, you guys really just need to know 1 minus beta, but it is kind of helpful to visualize where we get beta from. Typically, when I ask you guys to calculate power, I will tell you what power I want from you, and then you kind of fill in the rest of the information in our, we actually have a program that will do this for us. If power is too low, that decreases your chances of detecting significance. In other words, non-significant results may mask true significant differences. So if I have an 80% chance that I'm going to correctly reject the null hypothesis, I have a 20% chance that I will make a type 2 error. In other words, I have a 20% chance that I'll accept the null incorrectly. If I accept the null when the null is actually false, I have misidentified an actual significant difference. So that's kind of what this area means here. The best way that you can increase power is increase your sample size. Increasing your sample size, you guys will notice when you work on your practice problems, is going to narrow your confidence interval, which means when your confidence interval is narrower, it's easier to reject the null when the null is false, right? Because the more precise your confidence interval is, generally the more area you have outside of that to prove or disprove that the null hypothesis is true. Do note, though, because I do have sometimes people have confusion with this, that alpha doesn't change. So sometimes people think like, oh, if the confidence interval is decreasing, that means that alpha is increasing. No. The confidence interval is based on a level of confidence. The level of confidence is set a priori, and the level of confidence is directly associated with alpha. The actual interval values are not dependent on alpha. So, rephrased, power is a test's ability to detect a real effect in a population based on a sample. In our truth table, it's the probability of correctly rejecting the null when the null is false. And we identified that power is 1 minus type 2 error, or 1 minus beta. This is going to be dependent on 4 different factors. And you guys will get to experience this when we work in our power analysis. But it's going to be dependent on alpha, because these two things are kind of mutually exclusive, right? One based on accepting, one based on rejecting. So alpha is important, particularly when we're looking at the difference between two means or the difference between a sample and a population. That difference is also important. The standard deviation or the variation within both groups is important. We also need to know the sample size, because we know increasing sample size is going to help improve power. Okay, so that's kind of, all of these affect power, but sample size is the most easily manipulated one to improve power. So when we calculate this, let's visualize a distribution, and let's say that this is a distribution for a control group for a set of data. Okay, and their sample mean lies somewhere within that distribution. The control group is usually going to be representative of the population, so we can reasonably say that our control group is basically our population, right? Or it's the most representative of what our population would look like. With this, we set a level of confidence, and from that level of confidence, we can identify what alpha is. Okay, now remember, because we have a two-tailed test, alpha is actually divided by 2, right? So if you wanted to add that, you can. But within this area, right, if we take our experimental group and their group mean lands within our confidence interval, we would accept the null hypothesis and say that the intervention that we applied to that experimental group did not work, right, or that the intervention had no effect, such that the means of the experimental group and the control group are the same. or relatively the same, or they came from the same population. If our experimental group mean lies anywhere within our regions of rejection, we can reasonably say that with whatever the amount of error we were willing to accept, our experimental group is different from our population. Okay? Or our experimental group is different from our control group, which is representative of the population. So, the distance from our mean of our control group to alpha is a z-score. So we'll just call that z alpha. Okay, and then in our case, let's say we were using a 95% level of confidence. We know that alpha exists plus 1.96 standard deviations and minus 1.96 standard deviations from the mean. So if we were using a 95% level of confidence, in this case, z alpha would be 1.96. Now let's say this is our experimental group distribution and our sample mean for our experimental group landed over here. This black axis maybe just represents possible values of our dependent variable that we measured. Okay. So what happens is you see that there is some degree of overlap between our distributions, right? On one side of this overlap, we have beta, okay? And you can see beta and alpha are kind of exact opposites of each other. So if, in fact, we made a type 1 error, right, and we said that our experimental group's mean was significantly different from our control group mean, like we accepted the research hypothesis and rejected the null, the chance that we made an error is alpha, right? Because we rejected the null when the null maybe was actually true. Okay, so outside of our region of rejection when it should have been inside this area. Beta is the opposite. So right in this area, we have the probability that we are going to accept the null when the null is false. Okay, so you can see out here where this sample mean landed, we should reject the null, right? But this beta is the probability that we would have accepted the null because it's within these two yellow boundaries, right? Probability we would have accepted the null when the null is actually false. So you're kind of looking at where this region is shaded in reference to these two curves. But we can also represent beta as a z-score as well, and that is the difference from our experimental mean to this intersection between beta and alpha. So we call this z beta. And the area, again, is the probability of type 2 error. So if you wanted to, you could say where or what percentage of type 2 error am I willing to accept? Look that up on a z table, and that would be the z-score for beta. That one in particular, you don't need to divide by 2. Dividing by 2 is specific to alpha only. We also know that 1 minus beta is what power is, right? So this area represents the probability that you have rejected the null hypothesis, or that you accepted the research hypothesis, right? You rejected the null hypothesis when the null hypothesis is false. Okay, so hopefully this figure somewhat makes sense to you guys. So this kind of is just everything that we just described in words. I have this last note down here at the bottom to evaluate where z beta is compared to the experimental mean to decide if you should look up a positive or negative z-score. Usually I will give you power, so if you're willing to accept 80% power, that means beta should be 20% or less. Okay, 20% or less because, again, you don't want to introduce more error, you want to get rid of it. Generally, you can either look up 20% or 0.2 in the z-table, and you should get the same result as if you looked up 80% in the positive z-table. Both should give you the same number. We said that power is most affected by changing the sample size. So usually when you do a power analysis, you are determining how big your sample should be. How appropriate your sample size is kind of dependent on several factors. So how precise do you want to be? If you want to be more precise, you usually want a larger sample size. Less precise, a smaller n is fine. How sure do you want to be of your answer? If you want to be, again, very precise or very sure, a larger sample size is usually more desirable. How much variation is there in the population being studied? Okay, so this is the other factor we had mentioned at the beginning of our power discussion. Right, if there's a lot of variation in your sample, the more people you have, the better. Right, because the more people you have, think about your standard error of the mean, right? Standard deviation divided by sample size. The more sample, or the larger your sample is in the denominator, the less affected that standard error is going to be by the high variation that could potentially be existing. The last thing to consider is how small of an effect do you want to be able to identify. Okay, the smaller the effect you want to identify, the larger the sample you're going to want to have. Right, the larger the effect, the smaller the sample. So that kind of, again, goes back into how precise you want to be. In this slide, I've kind of linked a YouTube source that explains all of these things pretty well, if you want to watch it as a supplement. Using that information on what affects sample size, we can actually look at the formula that we use to figure out sample size. Again, usually we're going to use this when we are looking at the difference between two sample means, which is why I have two sample means here in the denominator. But you can see we use, right, a variation or a standard deviation. Usually this is going to be pooled between the two groups. We have how far away, or basically the value associated with the probability that we'll make a type 1 error, and the value associated with the probability that we'll make a type 2 error, and that's divided by the difference between the means. Doing this all together should give us the sample size that we need at the desired power we want. Okay, so usually, again, alpha is going to be set prior to, so if we have an alpha of 0.05, right, our z-score would be 1.96. For 80%, I want to say it's like 0.85 or 0.84. But again, we figure out what's the power probability that we want, and then we find what z-score is associated with that. Last thing, if again you're looking at power on the z-table, you always want to increase power, decrease error. Okay, so if you're looking at the positive z-table from 80%, you want to look at the value that is as close to 80% as you can, but not lower than 80%, because then you're jeopardizing the power level. If you're looking up on the negative z-table what beta is, which is the smaller percentage, right? So let's say usually we set it at 80%. That means that beta would be 20% or 0.2. When you look that up on the z-table, you would want the number that's closest to 20%, but not over 20%, because then you're introducing more error. So again, you always want to increase power, decrease error when you're rounding your values in your z-table. I don't always use 80% when I ask you to calculate power or sample size, so I like to make that note just in case. And we do go through some examples in the activities, so you should get some practice with that. When we calculate power and sample size in SPSS, these are the steps that we would use. So there is a power analysis. We can compare means as an option in the power analysis, and then we would choose the test that we want to analyze the power for. The limitations in SPSS, and we don't really do power analyses in SPSS because of these limitations is the types of tests that the analysis can be applied to are kind of limited. The results are not comprehensive, and they require population parameters, which may be unknown, which is usually the case. So it's really not that great of a software to do power and sample analyses in. The alternative that I like to use is G-Power, which is what you guys will be working with in your activity this week. And that allows you to have a lot of different starting point options. You can choose a lot of different types of tests that you would want to calculate power and sample size for based on the number of groups you're comparing. And all around, I think it's a really nice program. It's pretty user-friendly, so you shouldn't have too hard of a time with it. But all of this kind of culminates into where we're headed after the first exam. So this module kind of concludes what we'll be working on for the first exam. But when we come back after exam 1, we're going to be looking at what types of tests we are wanting to use based on the study design we have created. So big questions that you have to ask yourself are what types of variables are being dealt with, right? Do we have non-parametric data or nominal ordinal data, or do we have parametric data or ratio or interval? So classifying your variables is very, very important. How many independent and dependent variables do you have? Okay, if you have 1 versus 2, do you have parametric independent variables and parametric dependent variables, or parametric dependent variables and non-parametric independent variables? Right? How many levels of a given independent variable do you have? And if you have multiple ones, how many levels are in each of your independent variables? And then the last question is, who are we measuring? Right? Do you have a within subject or paired samples or repeated measures test where the same subjects are measured for each independent variable condition? Or do you have between subject design where you have different subjects measured for each independent variable condition? The last question we usually want to know is, do we meet test assumptions? So do we have a normal distribution of our sample? Are there any outliers? Did we randomly sample successfully? Do we have equal variance between groups? That'll be more important when we get there to like t-tests and ANOVAs and stuff. But assumptions are going to start being really important. Each assumption has its own p-value, which I commented you usually want assumptions to be a p-value greater than 0.05. Right? But considering all of these 4 key questions, we can create this thing called a decision tree. And you can see it usually it's going to start with the dependent variable. So we assess if our dependent variable is parametric or non-parametric. In our class, all of our tests are going to have a parametric dependent variable. So you should never get the classification of a dependent variable wrong, unless it's between like ratio and interval, but those are your only 2 options. For our independent variable, sometimes we will have parametric independent variables in the case of regression and correlation. Other times we will have non-parametric variables in terms of t-tests and ANOVAs. Number of independent variables if we're working with ANOVAs or factorial ANOVAs. How many conditions or how many levels we have of that independent variable will tell us if we're using a t-test or an ANOVA. And then the type of sample that we're working with will determine what type of t-test or ANOVA or factorial ANOVA, because there's 3 different types there that we're going to be using. So any of these tests that are in white without a red check between them are what we're going to be working on for the rest of the semester post-exam 1. I know it seems like a lot. I apologize, this lecture was a little bit longer than I wanted it to be, but hopefully I gave you enough examples or restated things enough that at least one of the ways I mentioned it clicked. As always, if you have questions, please let me know.